I'm very happy here to welcome Quran's very own Anupam Gupta, who is going to give a talk on chasing Convex bodies. I think I could imagine Anupam running after a ball or something.
Pretty much that.
And I misplaced my short 40 minutes introduction. Professor Gupta, so let me just mention that he was at CMU for some time before, and he's now here at Cohen, and we're very happy to have him here. And let me let him speak.
Okay. Thanks, Boris, and thanks everybody for being here. Yeah, today I'll talk about the work that's somewhat older. So it's not hot off the presses, but there's still some interesting questions to be answered out here, and I'm hoping that some of you might be able to give some ideas. Okay, so this is work with a bunch of people, some of whom were at CMU at the time, and others, we started working and then we realized that we were working on similar projects and we merged forces. So anyways, I'll give you a sort of a broad idea of these things, and please do ask questions if there are. Okay. So the general idea of the problem is very simple. You have an algorithm, so it's an online algorithms problem. You have an algorithm and you control a point, initially, let's say the origin, always, and it's in d dimensions. And at any point in time, the convex body arrives, and you have to move your point into the convex. And that's it. This body arrives, you move it there. What do you pay? You pay the distance you travel. That's it. Okay. And then another convex body arrives, and then you move your point into it. And then the third one arrives, and you move your point into it. And of course, you get to choose which point you want to choose inside the convex body once it appears, because your goal is to minimize the sum of all these distances that you travel. So in some sense, there's a trajectory that you're taking, and you want the shortest trajectory. The problem is you don't know the future. So when you see a body, you don't know what the next body is going to be. So you do what you can. That's the problem. So this is the algorithm's cost, in this case 14. And now what do you compare against? You compare against the hindsight optimum. So at any time t, you look at all the bodies that have appeared so far, and you find the shortest trajectory which satisfies these constraints. And that we call opt. And notice that opt can be smart about it. It can choose this point which hits both K2 and K3. It can be smart about it. And so opt in this case is 11.
So it has to hit them in the same order, right?
It has to hit them in the same order. Yep. So this is called the competitive ratio. The competitive ratio of an algorithm is the cost of your algorithm to the optimum cost. Of course, you are paying more than the optimum, or no less than the optimum, because it's the optimum. And you're looking at the worst case possible input sequence. Okay, so that's the problem. And you want an algorithm with small competitive ratio. You want it. Okay. This problem was proposed by Friedman and Linial in '93. And maybe I won't spend time motivating this thing. One thing I will say is that this is a common generalization of a whole bunch of problems in online. So online algorithms is this whole business of you get requests online and you have to make decisions before you see the next request. And you can capture, if you've heard problems like paging or K-server or solving linear programs online. This is really, you can think of this as solving a convex program. Okay? So it's a sort of a broad generalization of a bunch of problems, and any results you give here translate to a whole bunch of settings. So we are interested in this, but frankly, I'm interested in this because it's a really cool, nice, clean problem, very crisp. Good. So that's the problem. I want to minimize the sum of distances traveled subject to these constraints. And for about half the talk, I'll talk about a special case which will be important for us. It will be the nested case. And the nested case is just that simple. that, the next body is always subset. So this is one possible thing. In this case, you'll notice the algorithm I'm running is just the projection, just the greedy algorithm. Just move to the closest point. You don't have to use that algorithm. Here's the thing. And this is the cost of my algorithm. Now, of course, if you look at a nested case, it's easy to figure out what the optimal is. You just look at the last body and you just move to the closest point in that. So you just project onto that body, and that's what you want. Now, of course, at any point in time, the closest body changes. So you have to take that. Okay. So there's a nested case and there's a general. And in some senses, looking forward, what I'm going to do is I'm going to give you algorithm. I'm going to show you why, give you some intuition for this thing, but then I'm going to show you an algorithm for the nested case, and then we'll show an algorithm. Just recapping. Convex bodies arrive online. When you see a body, you have to move into it, minimize the total distance traveled, compare yourself to optimum, compare your ratio. You look at the nested case, and we want to get, okay, what's our goal? We want to get comparative ratios which are independent of the length of the sequence. I would like this to be just dependent on the dimension. That's more or less that. Any questions about that? We good? Good. So what can they? So in their original paper, Friedman and Linial gave a very simple lower bound. And the lower bound was, basically in D dimensions, you can't be better than the square root. Halfway through the paper, they switch from N to D, but in D dimensions, you can't be better than square root D. And it's so simple. Let me just take it. So let me show you the two-dimensional example. It's it generalizes to D dimensions. So basically, here's the idea. Initially, you are sitting at the origin, and then I'll tell you. In fact, I'll tell you up front. It's going to be a nested instance, and eventually you're going to end up at one of the corners of this cube. Square it.
But you're going to end up meaning the sequence is going
The sequence is going to end up putting you in one of the corners. Okay? So what am I going to do? Initially, you are sitting at the origin. I'm going to give you one of the facets. Now, where are you going? You go to the, essentially, if you deviate from the middle of this line, I can either give this point or this point. So essentially, you have no incentive to go anywhere else but the middle of this point. You can make all this formal, but it's easy. And then I'll give you one of the corners. And then you move there. You paid square root. You paid 2, where the right answer was square root. Scaling convex bodies. Ask questions if you realize you don't understand. Okay. And in general, in D dimensions, you should just move to that corner, whereas I'll make you go the long way. I'll make you pay the L1 distance, whereas you should pay the L2 distance. Oh, by the way, wherever I've written down norms, I'm implicitly assuming a Euclidean norm. You can talk about the problem for various norms, and results are known, and I'll try to indicate which results are known for general norms, which results are known for Euclidean, but right now just keep Euclidean. Okay. Lower bound of square root D for Euclidean. In fact, you can show a lower bound of square root D for any P norm, any LP norm. But, maybe let's just keep it simple. Okay. Good. So you can't do better than square root D, but can you do anything? So what Friedman and Linial, this paper, this is from the original paper, what they showed was in 2 dimensions, you could get a constant. And with a somewhat careful, sophisticated construction, which frankly, I don't quite understand. So I should catch Nati sometime and ask him to explain. And they asked a question, for general D, can you do something? And their definition of chaseable just means that the competitive ratio should be dependent only on D. And so they asked the question, this would be made the conjecture, in fact, that for any family of closed convex sets, it's good. So this was 93. The work that I'm going to talk about was now a few years back. I was just realizing that I'm giving you somewhat, fairly stable from 2020, but it took about 27 years to resolve this, and it's there was some amount of work, but yeah, some point ideas started cascading, and then boom, we got the result. So what I'm going to talk about today is I'm going to prove this conjecture, and I'm going to show you. Just to give you some information, I'll first show you that the greedy algorithm is not so good in general. Then I'll show you a solution for the nested case. In fact, I'll show you two solutions for the nested case. And then I'll show you how to solve the general case. So first, the greedy algorithm. So what's the greedy algorithm? The greedy algorithm just says that you're sitting at a point. You get a new convex body. If it contains your point, you don't have to do anything. If it doesn't contain your body, you just move to the closest point. So let's imagine you were sitting at that point on the left out. And now I'm going to give you this body. I'm going to project onto it. And I'm going to give you this body. I mean, you see where I want to make you go run circles around. Whereas what should you have to? Just go to the center. Right. No surprises. Well, maybe, yeah, okay. So unbounded comparative ratio. Opt is just this distance where I make you go around.
Why run you around?
So I've just shown you one round out here, and then I'll just good. By the way, it's an interesting thing, and it took us a little while to prove, and we had to use some technology to prove this. Is that for the nested case, you can actually show exponentially in the output, and this is type. It's yeah. I don't know of an elementary proof, so I'd love an elementary proof of this, but
It's a bound, it's an upper bound.
it's both an upper and lower.
Oh, okay.
I mean, I might be cheating a little bit. It might be d to the d. I forget exactly what the thing is, but there's an upper and lower bound, and they're matching to within the appropriate, big O upstairs. So what I want to do is now I want to focus on the nested case and give you a poly D result. Two poly D. And then we'll talk about it. Because somehow I think, in talking to people, it seems like somehow understanding the nested case was not articulated as a problem before 2019. In fact, I remember being at a workshop where this problem was discussed, and we were like, oh, how about the nested case? And we were like, oh, we haven't studied the nested case. Think. But anyways, good for us. Okay, so the nested case, I'm going to give two algorithms. One is called recursive centroid, and the other is the standard point. And I know some of the students are here, so good. Yeah, there'll be interesting sort of ideas and definitions. Some of you might have seen this before, some of you might not. Okay. Good. Good. For the moment, let's focus on a special case. The special case is my original body is going to be the unit body. And remember, in the nested case, right? So nested special case or special case. So it's the original body is the ball, and then I'll give you a bunch of nested convex bodies. And you're sitting at the origin, at the initial. Opt is a constant. In fact, it's 1 at most. All you have to do is you have to give me a solution which pays f of t, some function, times 1. It's up to scaling. This is the problem I want to solve. And I want to claim that any algorithm for this special case solves the general nested. And maybe let me give you a very high, high level hand wavy proof of this thing, just at least convince you that we should be true. Suppose I knew that the optimal solution was the optimal solution. Suppose I told you that the optimal solution value is between R and 2R. Okay. So what I'm going to do is I'm going to run the algorithm, this algorithm, on the 2R. Okay. Until, how much will I pay? I'll pay 2R times whatever this function f of d is. So everything scales, right? Okay. Until what happens? Until finally, my convex sets, which are nested, stop intersecting this 2R. But if they stop intersecting this 2R ball, I have a proof that the optimal solution must have paid more than 2R. So I'll say maybe the optimal solution pays between 2R and 4. I just come back to the origin and run this algorithm again on the 2R, 4R values. So it's kind of this guess and double idea, which is very, simple at some level, but kind of powerful. We kind of good with this. Good. Okay. So here's the problem I want to do. I'll try not to do that too often, but
It's all right.
it's so the problem is this boundary. Okay. Everything's in the unit ball, and these sets are shrinking, and I need to change these shrinking. One more thing. Suppose I reach a point where my sets lie inside a ball of radius half. I started with the ball of radius 1. After a little while, I realized, not to scale, but whatever. Inside a ball of radius half. I can forget everything I know and just recurse on this part. How much will I pay? F of d times half. What did I pay before that? F of d times 1. But it's a geometric sum. So all I have to do is, in some sense, localize where I'm going. As soon as I can be inside a smaller ball, constant factor smaller, I'm going. So basically, that's the name of the game. Start with the unit ball, and finally, as soon as you're guaranteed to be within, a half ball somewhere, you say, okay, I'm done. So this is the problem. I want to reduce my body size. In fact, I want to reduce my body diameter. Don't quite know how to reduce my body. Okay, whatever. Here is something I can try to do. I can try to reduce my body volume. Seems kind of weird, but if you've seen algorithms for sort of convex optimization, ellipsoid method, things like this is often how they go, and this is how we came about. So what I'm going to do, this is my algorithm. This is the proposed algorithm. It's going to be a lousy algorithm, but we'll fix it. Okay. So the algorithm is if the current point is inferior, then look at your current set and move to the centroid. Now, my current point is infeasible. I need to move to the center. Why is this good? And it's this sort of fact. And this is Grunbaum's theorem. Some of you have seen it before. So basically, this new convex body lies in this sort of on this side of this half space. And any half space that cuts off the centroid of a convex body cuts off the volume by at least one. So very, very useful. Every so often I have to bust it out. The Grunbaum's theorem says take any convex body, take its centroid, any hyperplane through the centroid. The two sides are roughly balanced. 1 over E, 1 minus. The bad case is the simplex. If you take the simplex, anyways. Okay, Grunbaum's theorem. So what's happened? Every time I move, the volume of my current convex body has shrunk by half. I'm making great progress. in volume. Remember, I want to localize the point in radius or diameter, but I'm making progress, which may be okay, maybe not. But it's not, and I already told you the algorithm is lousy. And here is an example where just going to the centroid is bad. And this example will be useful when later on. Okay. So you were sitting here. This is the centroid of the original box, and I give you this slopy model. You move to the center, and I can give you a slope so that you'll move a constant fraction of this way. And then I'm going to level it out. I'm going to move right back. And then I'm going to give you another slopy guy such that you move again a constant fraction. I'm going to make it zigzagging mad. What should you have done? You should have zooped just one. So you're being silly.
But also in your rotating sector case also it would be bad, right?
Good. So that was not a nested.
Right. Yeah.
Yeah. So nestedness is crucial for this algorithm to even have any chance. Yeah. I can give you an example. Just two balls which almost touch each other. Just move to the centroid. Bogus. Good. Nest. Yeah. So even for nested, the centroid algorithm. Yeah. But it's not there. So let me give you an idea of why it's not there. So suppose you started with the ball and you started playing this out. The volume is shrinking, right? So the volume is shrinking, what can happen? Either you get a much smaller ball, in which case you declare victory, or you get a pancake. The diameter is large, but the volume is. But then I want to claim that there must be a thin direction.
You're walking in the plane.
In the plane. So basically, this is essentially a two-dimensional body. It's not a three-dimensional body. So we should treat it as a two-dimensional body. It's exactly what you said. So what I'm going to do is, I'm going to essentially project it out and run the centroid algorithm on this two-dimensional body. There's a slight catch. The body is actually three-dimensional. So if I look at this body from the side, there is a sliver. I mean, it's 1 over poly d thick, but it's still a sliver. And in general, this is some k-dimensional subspace that I've projected out. So every point here. Now, I don't have enough pictures with this one. It takes forever to draw pictures. I wish these LLMs would become much better and I would tell it what to do. So look at a point out in 2 dimensions. It corresponds to a little interval in the 3rd dimension. So what am I going to do? On that 3rd dimension, I want to play a 1-dimensional algorithm until that portion is empty. So essentially, it's this pancake, and I'm now guaranteed that the center of the pancake, none of the points lie in KT. Okay. So if none of those points lie in KT, I can take a separating hyperplane, which is along this 2 dimension. And I'm making progress in the body, a 2-dimension. A little high level, I'm waving my hands around. But once you see this formalizing, this is not there. It requires a little bit of work. Basically, thin dimensions are thin enough that the total movement in those thin dimensions is going to be, it's like 1 over poly d times f of d. F of d, let's say d squared. So 1 over poly, 1 over d to the 10 times d squared is time. It's much, much less than. So here's the general idea. Start playing the algorithm, just halving the volume. Either you reduce the diameter, in which case you're great. Otherwise, after some order log d steps, you'll get a thin direction. Project that direction. For each of these log d steps, you paid 1 at most. Okay? Now on the lower dimensional space, play the thing again. Then each step now requires you to play a recursive problem on a much, much tinier one. Not going to cost you. Yes. Frankly, it's not difficult. It's just so formally writing it down, you guys will follow. I'd rather show you something more fun.
But it's not giving you D times that of D.
It's not giving you so it's giving you 1 over poly D because the scale is so much smaller.
Right, but you mod out each of the D directions, right?
Exactly. So what's happening is each time, so now each step in this D minus 1 dimensional, in this 2-dimensional thing, how much is it costing me? It's costing me 1 over poly D times
I see, that's the
D
concept.
squared
Yeah.
plus whatever movement, which is pretty much it. So you can do this from first principles. The proof is a little messy, but it works out. Or you can write a very nice potential function, and you can show that the potential function is controlled. Basically, every time you do a projection, you have to look at the D minus 1 dimensional volume instead of the D dimensional volume. So that increases, but on the other hand, Grunbaum cuts are decreasing the volume. It's a little delicate dance, but not too bad. So this was the recursive centroid algorithm. Even though I say so myself, it was sort of cleaner. I like it. And I thought, what can be cleaner than this? Oh. Okay. This was for the nested case. What about the general? So then we thought about this for the general case. And so me and my students, so CJ Argy was a student with me. We were thinking about this. And the other group was also thinking about this, and they cracked it first. And they had this substantial generalization because another one of those things where this one I do understand, but it's like it's intense. Let's put it this. And it gave a 2 to the order D comparative algorithm to the general case. Very nice. Yeah. The Friedman linear conjecture argument. And maybe we'll talk about it another day because instead I'm making good progress. I'll show you the others. So what I'll do is I'll give you a simpler and better. And so this is work again with CJ, with my other students, Guru Ganesh and G.A. Tan. And independently, Mark Sellke came up with a similar algorithm, almost the same algorithm, but with very different perspective. I'll talk about it. And I'll show you this algorithm that's already compact. So this is improving on the nested case as well. And it's, this kind of just completely. Oh, I shouldn't say completely. I'll come. Good. And so there are 2 proof ideas that are. So there's 2 ingredients. One is called the Steiner point, which I don't know how many of you are familiar with the Steiner point. I wasn't familiar until I started working on this thing. And this will give you a new nested algorithm. And then I'll reduce the general case to the nested. So let's define this time. That's one thing to remember. I mean, you've already seen Grunbaum's theorem. Now, there's a second thing to remember. What's the Steiner point? The Steiner point is the average of the extreme points. So take a random direction, look at the extreme point of this convex body in that direction. Just average.
So this corner doesn't count because that's measure 0, no?
Which one?
The corner.
This one?
Yeah, that's measure 0.
Actually, what it will give you is it will give you for all these directions.
Then it's not standard for it. It's not that standard point for triangle.
So maybe let me draw it out here if it helps. So what's the center point of the triangle?
Yeah, some of, minimum some of these words, right?
No. So basically, I guess what I'm saying is just look at the sort of normal cone out here.
Yeah, then that's not limitation.
Oh, I see. Interesting. Interesting. So this is the definition that I got from
Okay. Wait. So in high dimension, then take Gaussian curvature or?
okay, in high dimensions take the you can so maybe I can write it as you integrate over the multivariate Gaussian of the R max or X dot G. So look at a random Gaussian, so it's a random direction. Look at the point in my convex body, which is the maximized. So if I took this direction, then this point would be the max. Okay. So that's the step. At least the center point that I know of. These are clearly all these things. Every famous name has a point associated with it, and they're not unique. So, but. And so the new algorithm for the nested case is it's going to be embarrassingly simple. Just move to the side. You don't have to even worry about whether the point is feasible for the new set or not. Just move to the side. Will be very wasteful. The body is moving slightly, it's okay. But remember, it's nested. Apparent convexity is important. Convexity is super. Without convexity, your whole strike frame. So it actually, it's a sort of nice story. Apparently, Bubeck was giving a talk at in Tel Aviv, and he showed our recursive centroid algorithm, and Klartag came and said, do you know about this time? And we didn't, and we looked it up. And then they wrote this paper together. And the claim is that this algorithm is decomparative for the nest. So, it was instructive for me to see this bad example that we did earlier. You remember this trapezoid bad example that we had? The center point of, let's say, the original body, it should really be in the middle. Use your imagination. This is really the middle of this. Now I give you this query. So what am I doing? I'm moving to the Steiner point, which is really the average of the corners weighted by the normal cones. By the volume of normal cones. So you'll move to maybe that. Whatever. Now you're back again, so you'll move back. Sort of important point is that if you try to do this example, the next slope can't be very large. So now the normal cones are more balanced. And the thinner the body is in some direction, the normal cones tend to be more balanced in that direction. And so you don't move that far. And you actually sort of kind of control. And I often, in my mind, I think of this as like a smooth version of this recursive.
So the idea is it was like half of the this Gaussian measure on the right and half of the on the left, right?
Pretty much. It's so out here it was maybe half plus epsilon. Yeah. But that epsilon is getting better and better, and after a little while, totally. When it's competitive, it's memory less as well. So you don't have to remember.
But this behavior is very similar to the previous algorithm, right? Because
totally. So I think of this as like the smooth version, the right version of that. I thought it was the right algorithm, but So let me give you the proof of decomparative. It's one page of algebra. This is the only algebra that I have in the whole thing. But you'll see how ridiculously. Okay, by the way, I should say that this proof is from this paper of Bubeck, Klartag, etc. And it follows, I mean, the standard point is understood because it's what they call a Lipschitz selector. For every convex body, you want to give a mapping from convex bodies to points inside. Such that if I give you two convex bodies, the distance between their mapped points should be Lipschitz in the Hausdorff distance between. So I want to give a mapping from convex bodies to points inside those convex bodies with the following property, so that it should be Lipschitz. Lipschitz in what sense? That f of k minus f of k prime should be at most the distance between k and k. And the distance is the Hausdorff distance. And now the question is, it's not quite the distance between k and k prime, but some alpha times k and k prime. And the correct answer is square root d for that problem. And it's been well studied. People look at that. It's somewhere in the survey by Benjamin and Lindenstrauss, other stuff. It's lots of nice problems. But anyways, I digress.
So the map is the map to the standing point of the body?
The map is the map of the standard. And that is the optimal one, and they show that both are optimal. The proof is similar to what I'm going to show out here. And of course, Boaz knew about this. Yes. Okay. So let's give the definition of standard point one more time. And I'm going to define what people call the support function. Given a theta and a body k, this is the maximum value. It's just saying, theta is the objective function and k is the body. What is the maximum linear form by linear order? So this is a scale. And if you take its gradient with respect to it's some algebra that it happens to be the argmax in that direction. So what I wrote out there, the argmax of that thing, you can just replace by this compact. So that's the standard.
It's like kind of standard of surface of the wall body, right?
It's I'm not completely sure. Yeah. Okay, G is the Gaussian. Okay. And here is a fact that you can prove. Call it a fact. Initially, when I saw this, it seemed like magic, but familiarity breeds contempt. So this is a vector, right? H of k by itself is a scalar, and G is a vector. These two things are equal to each other. Initially, you might think this is obvious, but then you think, why the heck this is true? But this is true. And I can give you two proofs of this. I'm not going to give you either one. One is you can use the divergence theorem, which, of course, it seems very mysterious to me, divergence theorem. But it's really integration by parts, which at some level, the divergence theorem is integration by parts. So it's really, you do Gaussian integration by parts to get this equal. If you look up CJ argues thesis, we actually put a proof out there because it's nice and cheap. Good. So there's two definitions. I mean, it's equal. Sorry, you can hardly see what's written, but anyways, this is kind of visually intuitive. This is the average of the corners, weighted average of the corners. So by the way, this already shows that the standard point is the point inside the body. This weirdo definition gives you no indication, no such thing. But since they're equal, this is point. And this is algebraically there. So we're going to use this. So what's the value? Take a random Gaussian, look at the maximum value of the linear form inside the body K. This is a scalar times this vector. average overall. Good. Okay. So the proof of decompetitiveness, there should be a little Harmonic symbol out here. Pain is bounded. So that's the sum over all times t of the distance. So let's write down the definition. Xt is really g times the support function of the t minus first order. And I'm just using, instead of writing h of k of t, I'm just writing h. By the way, let's observe one thing out here. If a body is smaller, the maximizer. So actually, let's go back. This object. If I take this body and I replace it by a smaller body, the maximum is only going to go down. Okay? So this maximum is bigger than this maximum. This term h is no smaller than this because the body is shrinking.
Even if we point outside, right? If they,
no, ask me again.
so the smaller body can be outside of the.
Yeah, so the smaller body is just, it's contained inside the bigger body. I mean, these are
Yeah,
nested.
but the point, the center point can be outside, right?
No, because if the advantage is we already just kind of argued that the center point is always inside, so. Okay. This is bigger than this pointless. Okay. Good. Linearity of expectations. This is I just combine like terms. So to speak. Okay. Remember, ht minus ht is ht minus 1 minus ht is non-negative. We see a norm and an expectation. Push the norm inside the expectation. A kind of convexity. No, yes, kind of inequality. Oh, by the way, one thing I did was I pushed the norm inside the expectation, and now I use the fact that this is non-negative to pull this. Okay, so this is non-negative. And now I have a summation over t sitting outside. I can push that. It's just sort of algebraic manipulation, and you have to do it in the right order. But of course, all algebraic manipulation, you have to do it in the right order. But so now you're summing over all t's of the support function values, non-negative differences. So there's a telescoping sum. So this is initially at 0, and whatever the final value is it's non-negative, throw it away. Actually, I think you might need, I might be cheating a little bit. Good. Maybe a factor of 2. But actually, you can save everything, but it's forwards. So it's the expectation of g times h0. What is h0 of g? What's the original body? It's the ball. The h0 of g is always 1. Forget that. Sorry. H0 of g is always the norm of g because it's the unit ball. So it's the norm of g. So there's the norm of g times norm of g. Norm of g squared. Where did the R come from? Sorry, no, I don't know. This is the unit ball. Forget the R's. I was doing it for the R radius ball, but it's the unit. Forget it. So it's norm of g squared. Norm of g squared, you know what the expectation of norm, g squared for a Gaussian is.
So you don't need the essential Gaussian measure, you just need any measure on directions. And then to choose the central point according to not necessarily Gaussian. Right?
So good. So I did not need the Gaussian measure.
Uniform.
Good.
Uniform.
Exactly.
Any measure works.
Exactly. With the Gaussian somehow is sort of my favorite measure.
Uniform.
Exactly. My favorite uniform. My favorite, maybe my favorite measure period, but also my favorite uniform. Good. So that's If the algebra was too much, come back here. Always forgive. Let's move to the standard point of KT. This is the deep imperative algorithm. Good. Okay. Good. So I told you about the standard point, and we gave a new nested algorithm. Then you're like, oh, how do you extend the standard? So for that, after some misses, we got this idea, which I kind of like it. Good. Let's go back to the setting. You remember we talked about this sort of guess and double idea. A similar guess and double idea will work in the non-nested case as well. Here's the problem that you really need to solve. If you solve this, everything else falls. What's the idea? I'll start with the R ball. And this time I'm sticking with R because I want to emphasize R actually. I'll start with the R ball and then I'll give you a bunch of convex sets. Now they're no longer nested. This is general. I guarantee to you that the optimal trajectory is of length at most R. So the optimum can never escape this ball because this ball is the R. The optimum is less than. Just give me a solution which costs me at most f of d times. And think of f of d as d. This is what happens. So, how do I?
But the bodies could intersect the boundary of the spot.
The bodies could intersect, but if I guarantee you that the optimum is within this thing, you can just throw away whichever part of the body is outside. Because if opt is not going to go there, why would we? If the body is completely outside this ball, we have a proof that opt can't be less.
No, that I agree, but your standard thing will go out, could go out, right?
Exactly. So good. So that's a very good point. Let's always imagine that our bodies will always take intersections with the R. So whenever I'm going to define a body KT, it's going to be defined with its intersection with R. That's okay. My whole world is the R. I should have said that each of these is a subset. Okay. We have 10 minutes. Oh, yeah. And in fact, we're going to, the proof is almost. There's 3. Okay. So first, you might say, oh, let's chase the Steiner point of KT. I give you this set, just move to the side. Crappy. So imagine the following thing, there are 2 balls. This is the same example as before. There are 2 balls which are just touching. I give you the first ball, you move to the center point, which is the center of this ball. I move to tuck. You keep moving back and forth. You should just really sit on that point in the intersection. Okay. Okay. So here's sort of the crucial insight. Let's define a set omega. It's like some imaginary set. And these are after time t, omega t is the set of all x's where opt might be hiding after seeing the first t. So remember, opt, these are all points x such that, the length that opt is traveling to reach x and satisfying all the constraints is at most. These are all the points where opt could be hiding. So before you've seen all the points, opt could be hiding anywhere in the R. But after you've seen, let's say, this weirdo thing, you just look at all points which can hit this K1 and have the total length at most R. It's some kind of weirdo truncated ball. After a little while, it's this weird, object. Weird, but still nice. Two nice problems. These sets are convex, and these sets are nested. Convex is by picture. If you can get to y at distance r after hitting q1 and after this, then you can get any point. Yeah. Oh, omega, what's omega? So omega t says, look at all points x, such that if you sum up the total distance, that there exists a trajectory of length at most r, which satisfies all the inclusions.
What opt could have done.
What opt could have done? Opt could have chosen any of these paths and reached a point x.
So then I was completely, but R is known before or,
So imagine R is known before. We are going to do a guess and double kind of thing.
okay, yeah, this is what I, yeah.
Good. R is known. Good. So R is known. We'll start with the R bar and then we're going to shrink it down. So first, if you can reach y, if opt can reach y and opt can reach x, then opt can reach any point of the graph. You can define a suitable trajectory.
But this must rely on the bodies being convex.
Totally, totally. Good. If I give you more constraints, opt can be in fewer places while paying at most time. So these sets are nested. So I'm giving you a bunch of convex nested sets. What should you do? You should chase those sets. New idea, chase these nested convex sets. We had this idea.
Sorry, could you explain why it's nested?
Okay, so what's the definition? The definition says, look at any point such that it satisfies all the inclusions and can reach this point x. So if it could hit k minus, t minus 1 bodies, or it can hit t bodies and reach x, then it can clearly hit the first t minus 1 bodies and reach x. Just follow the same path.
How complicated can the boundary of this set be? Like those exponentially increasing or what?
Don't know.
You don't care about it.
I don't care about it. I think it's kind of complicated in the sense that, yeah, I don't know. But, you can ask the question, all these can be made, algorithmic questions can be posed for these things, but we'll come to that. I'll just talk about it first. Okay. So chase these nested convex. What's the problem? I'm chasing some stupid sets omega t. I want to chase sets kt. Why the heck is this Steiner point inside kt? Actually, so far I could have said use any nested algorithm to chase these nested sets. But then this statement would be false, patently. Xt need not be inside kt. But the Steiner point is in the right. Xt will be inside kt. And that's the key lemma, and then basically right. So let me give you a proof. And again, I'm going to wave my hands. What do I want to say? Omega t was this sort of where is all? Where in the world is all? And kt is the last body that lives. For simplicity, imagine kt is a half space. You can use, whatever separating hyperplane theorem, whatever you want. Doesn't matter. kt is a half space. I want to show that the Steiner point of this green object lies inside kt. It's suggestive the way I've drawn it, but it could not. So let's look at all and let's look at the definition. So what's the worry that the Steiner point lies outside? So let's look at any point which is outside in omega. What does it mean? It means there's a trajectory that ends up here and pays at most R. It's a valid trajectory. It ends up here. There's some trajectory. Look at the mirror image of this guy across this separate this hyperplane cube, defining cube. Okay. It's a valid trajectory. So whatever the trajectory definition was, must have hit KT somewhere. Boom, boom. Basically, whatever this length was, this part, I can reflect about this. Exactly. So this is a trajectory. Yeah. Oh, yeah. Okay. Sorry, I didn't hear you. Now I understand what you said. Good. So basically, I'm saying that whatever this part outside is, it's the measure. You reflect this whole part. It lies inside. So whatever omega t is, the part outside, its reflection is inside. And any self-respecting measure. This is where I wave my hands around a little bit. It requires a little paragraph proof. Any self-respecting measure must put the standard. And the standard point is a very so that's my proof package. Okay. Comment. This proof works for Euclidean norms. If we change the norm, by the way, so the previous Steiner point, the decompetitiveness I showed you, nowhere did I use. So I used the Gaussian there. If I wanted to do it for other norms, I would use a slightly different definition. It would work out. The Steiner point, you can define a Steiner point with respect to any norm. And then you can show that the algorithm is decompetitive. And there exist norms for which it's decompetitive is the best you can do, etc. So that's a very general algorithm. This proof that I gave you is very Euclidean. It uses reflections and stuff like that. What I can tell you is there is a version of this algorithm which is decompetitive for all norms. And basically, Mark Sellke, he knows more maths than I do. He came up with a definition which he calls the Steiner-Wald function. Ignore all this thing. But if you're interested in general norms, you should look at Mark's paper, and he nails the problem. So yeah, so very nice paper. It's the same idea, but two very different languages. Very different. Very well. Anyways, okay. So that's pretty much it. That's the order decompetitive algorithm for chasing convex bodies and general convex bodies in these dimensions. Maybe a couple more very quick comments. You can extend this. You can say, what if? Okay. What if your bodies are nice? Let's say they're lines, they're half spaces. Then you can get something. You can talk about, oh, I control 2 points. And now you give me a convex set, I can move any one of my points inside the body. It generalizes the other problems that we're interested in. These become much harder questions. And we know, such results are not. And finally, and I'll very quickly mention, you can change functions as well. So instead of giving you a convex body, I'll give you a convex function. You can move to any point. And now what do you pay? You pay the movement, plus you pay the function value at the point where you. So you say, okay, and this comes, a bunch of people were interested in this because it captures, kind of configurations of data centers, for power distribution and also for data centers. So very applied people were interested. Anyways, For us theorists, is a sort of very concrete open question. I'd love to solve it. I don't know how to do it. I gave you a D-comparative algorithm. I gave you a square root D lower bound. Let's close it. I don't know how to do it. For the nested case, there is an algorithm which gives you ordered square root D times polylogs. But it's very, again, it's like the recursive centroid. It's kind of complicated. I don't know how to make it generalized to the general case.
And D is typed for this time.
D is typed. So what you can do is you can say square root of D times log of T, the number of bodies. You can give a T dependent bound, but as P goes to infinity. What if the bodies are nicer? Can you do something like that? What if they're good? In the positive order? What if they're what if I give you a polytope, and at every point in time I'll tell you, oh, I'll only give you a facet of this polytope. You have to move to that facet, that facet, that facet. Fixed body, just different facets. Can you do that? Don't know how to do things. Some of these things I haven't spent too much time on. It might be interesting. I mean, it is definitely interesting. It might be easy. Practically. Yeah. And some of these ideas have connections to online learning. So those of you who are interested in online learning, there are some connections, but not fleshed out.